the continuation of thermal properties in matter. In this session, we are going to learn about what is black body and how can it be released, energy distribution curve, Newton's law of verification, and the experimental verification too we are going to learn. Let us see elaborately, students. Yes, next one is black body. See, the black body radiation, we can say that a black body is one which neither reflects nor transmits but absorbs whole of the heat radiation incident on it. See the diagram, students, and the absorb power of the perfect black body is actually unity. When a black body is heated to a high temperature, it emits radiations of all possible wavelengths within a certain wavelength range. See, the radiations emitted by a black body is, we can call it as black body radiations. The first diagram will shows the black body absorber, and the second one is a emitter. So these are the two different black body which we are seeing that. Okay. So the energy distribution in a black body spectrum, when a black body is heated, actually it emits the heat radiations of a different wavelength. Now, when the radiation of a particular wavelength has definite energy of a particular temperature. See the diagram, students. See, this will shows the experimental curves drawn between the wavelength lambda and the intensity of the radiation, right? So, it is emitted by a black body that is maintained at different constant temperature. Now, through that, we can understood some points, that is conclusion which is drawn from the black body spectrum. At each temperature, the black body which emits continuously heat radiation spectrum. Now, the energy is not distributed equally amongst all the wavelengths. You may see the graphical representation, right? And the energy which is associated with a radiation of particular wavelength is getting increases with the increase in temperature. And finally, we can say the wavelength, if suppose it is getting increases, the energy will also get emitted, increase, so that it reaches a maximum for a particular wavelength, lambda m, and again it decreases. See that? Yes. Newton's law of cooling. See, the rate at which a body which loses the heat by radiation, it is depending on the temperature of the body and the temperature of the surrounding medium and the nature and the extent of the exposed surface. So, we can say that the Newton's law of cooling statement, that is the rate of cooling of a body which is directly proportional to the temperature, that is differences between the body and the surroundings. Now, we can see the expression for it. That expression we can say that in the accordance with the Newton's law of cooling, that the hot water bucket that cools faster initially until it gets lukewarm after which it says so for a longer time, right? If suppose like you can consider a hot body at the temperature of T, and we can take T0 as the temperature of surrounding. So, the T we have taken, so the mathematical expression for that, we have taken any hot body that T is the temperature of the hot body, and we have taken T0 is the surrounding temperature, right? Now, then we can say minus dq by dt is directly proportional to T minus T0, or we can write minus dq by dt, which is equal to k into T minus T0, right? Now, this dq, which is equal to mc into dt. We can, respect with the time we have taken, means dq by dt, which is equal to mc into dt by dt. That is d by dt of temperature, change in the temperature, right? Now, we can compare these two equations, then minus mc into dt by dt, which is equal to minus k into t minus t naught, right? So, dt by dt, which is equal to minus k by mc into t minus t naught, which is equal to minus k into t minus t naught, right? So, the dt by t minus t naught, which is equal to minus k into dt. Now, we need that for integrating that both side only, we will get the whole work, right? So, we'll integrate it. Integration of 1 by t minus t naught, which is equal to dt. So, this 1 by t minus t naught into dt, which is equal to minus k into integration of dt, right? Or we can write this as log base e t minus t naught, which is equal to minus kt plus constant, right? C, right? So, this t minus t naught, which is equal to minus exponential power minus kt plus constant. Or you can write this as T, temperature, which is equal to T naught plus e power C and e power minus KT. So that the T, which is equal to T naught plus C into e power minus KT. Right. This will give the expression for the Newton's law of cooling. And see the diagram, that is graph, children, that the curve is showing the cooling of hot water with time, and this straight line graph between the log t minus t naught and for the time, which shows the slope which is equal to minus k, right? So, this we plot the graph taking the different values of temperature difference, that is del T, that means T minus T naught, right? Along the y-axis, in corresponding values, we have taken time T in the x-axis. So that we get curve and we are getting that straight line for log, that is T minus T naught into T. Right. So the experimental verification of Newton's law of cooling. See the diagram, students. Actually, this is consist of the double-walled vessel that is containing water in between that walls, right? And that next one is a copper calorimeter which is containing hot water placed inside the calorimeter, right? And two thermometers which are kept with the cork, which are used to note the temperatures. So, the two thermometer which is used for noting down the temperature. That means for the hot water of the calorimeter, then the T naught is the water between the double walled, right? Respectively, the two. Now, the temperature of hot water in the calorimeter is noted after fixed intervals of time period. So, you have to note it down each and every fixed intervals because we want to plot the graph for it, right? After every 1 minute, you have to stir it. So, the water will get gently stirring with the stirrer. Continue noting its temperature. Actually, still it attains a temperature about 5 degrees Celsius above the surroundings. Now, we can plot the graph between that log E, that is T minus T naught, with the temperature and the time. We will get a straight line, right? So, you can take in the x-axis the time period and in the y-axis that log exponential of T minus T naught. When you have taken means, you will get a straight lines. You can note it down the temperature, you will get straight line of graph, right? Yes, students, so far we have learnt about black body the black body radiation, energy distribution curve. These and all we have relatedly about the black body we have learned. And Newton's law of cooling, the verification of Newton's law of cooling with the experimental explanation part we have learned. You might have understood. Thank you, students.